Welcome to another video explaining the universe using the particle model. And my name is Bob D. Hilster, and I am your particle model guru. I'm revisiting a video I just recently made on the magnetic field or charge, and didn't quite do the job I would have liked. So we're going to revisit it and try to straighten things out. I got a comment from a viewer. This is his identity. That's his name. He states, first off, you should know better than making a comparison of a bar magnet to a battery. If you know anything about electricity and magnetism, you would have thought twice about presenting this video. And here's his real comment: an electric current generates a magnetic field. That's how it's done. All magnets are created by being exposed to an electric current. He's saying I'm being quite disingenuous. Well, I take comments like this seriously, and although I disagree with being able to compare a bar magnet and a battery, he does have a point about how magnetic fields are generated. And that is particularly one way they are generated. I'd like to point out, however, that when magnets are manufactured, when they get the material ready to get it set, just before it sets in and is magnetized, they magnetize it by drawing it over an existing magnet. And as they do that, according to the particle model, the G1 particles of the existing magnet are flowing through the new material. And then as that material sets, or cures, whatever it does, it traps these G1 particles, and the magnet becomes magnetized. So now, it's the G1 particle of the permanent magnet that is generating the magnetic field for the new magnet. G1 particle does it then. In the particle model, the electric current, in fact, is the flow of G1 particles. In both cases, the G1 particle is what establishes a magnetic field in a wire or an electromagnet, and it's the G1 particle that establishes a magnetic field in a new magnet. This video is my response to him, and I didn't think more about my statement that a battery has a magnetic field, and this is really what I want to address today. The next slide I will show indicates there is a force around a magnet that causes the compass needle to move. As you move the compass around, the needle moves, and there's something causing that. And there is a force around the battery that causes the compass needle to move. But then the question I'm asking myself that I missed last time, but does that really prove there's a magnetic field? I'm going to stop here again. When we first learn about magnets and how to use a compass to draw the line, I believe we're clearly saying that that needle is following the magnetic field there. So we get the impression that you can find a magnetic field by putting a compass and a compass needle there. And I'm going to say I'm not sure that's true. Okay, my question of the previous video was this: why are the forces around the battery and the magnet defined differently when the compass needle reacts the same way? Around the battery, it's charge. Around the magnet, it's a magnetic field. And yet the compass needle's responding in a similar way. And it would seem that nature shouldn't have to have two different ways of controlling that needle. Why would it choose two different forces? My answer was there really should only be one force, and the TPM suggests that the compass needle is controlled by the G2 gravity field, not by the magnetic field, nor by charge. That was my answer. That's what it was controlled. And now we're going to pursue this further. But now I have this new question: does the motion of the compass needle prove that there is a magnetic field? If the G2 gravity controls the motion of the compass needle, then the magnetic field need not be there, and it will move anyway. So if you make the assumption, now you may not agree with it, but if you make the assumption that G2 gravity controls it, then you don't have to have a magnetic field there to explain why it's moving. It's moving because of this. Maybe it's moving by virtue of both, but I'm making the assumption it's being controlled by G2 gravity. Well, I did this quite a while ago. I remember the first time I took the compass, put it around a battery, and I said, wow, compass needle moves. And I concluded a few years ago that the motion of the compass needle proved that there was a magnetic field. But it seems I could be wrong. The TPM suggests that there is a G2 gravity field around all objects, around the Earth, around us. There is even, you can even see, sometimes detect magnetic fields around our own body. The strength of the G2 gravity depends on the number of G1 particles in an object. That's an observation I've made working with light and gravity and electromagnetic forces and electrostatic forces and even circuits. I've come to that conclusion early, and it's pretty well held up. Now, there may be other factors, but generally speaking, I've been able to describe the function of things based on the strength of the G2 gravity depending on the number of G1 particles in the object. Magnet has a lot of G1 particles flowing through and around through it, generating a strong magnetic field. A battery is releasing G1 particles at a steady rate. It's a chemical action. Normally we call that a chemical action. And it can set up, based on that, a G2 gravity, but it's probably weaker, a lot of weaker for it, but enough to control the compass needle. The compass needle is sitting there in floating all by itself on a pin, center point, and it's very easy to move. You don't need a lot, and we protect the motion of that by encapsulating it inside the casing of the compass. But so you don't need a lot of force. The G2 gravity doesn't have to be very strong to move the compass needle. Okay, so then I'm still trying to find out, how do I prove there's a magnetic field around the magnet or the battery? Do the iron filing patterns, these are the patterns you see here, generated by a magnet or any other device, prove there is a magnetic field? Right off the bat, I'm saying yes it does. The only way the line of iron filings, and you see lines here, the black lines are the iron filings, and they separate. The reason you can see the lines is because the lines have a gap in between. If there's a gap there, it is because of repulsion in the particle model. Because we don't have charge and plus or minus attraction and repulsion, only magnetic fields repulse. So I claim, yes, these iron filings, they are magnetic. They pick up the magnetism from the larger magnet. So they are magnetized. That means that each iron filing has a flow of G1s around it, just like a straight wire does. It has a flow of G1s going through it, and around it. So this is how, my opinion, how the iron filings get magnetized. The red dots are G1 particles that are flowing around and through the magnet. Now remember, this is just a particle. It has no charge, neither negative or positive. It of itself has no magnetic field. It's just a particle. And it's flowing around and through the magnet. And when you first lay it down on the iron filings, some of these are going to enter, follow through, and then leave. Some will get trapped, some will get hit, but most of them pass right on through. Because the iron filings become magnetized when enough of these G1 particles pass through the iron and sets up G2 gravity around this filing, or a group of iron filings. I mean, it certainly, in the picture you just saw, doesn't look like one tiny filing. It looks like a clump of them. It sets up gravity around. Then it obtains a G1 flow around the iron filings, which means it's got a flow going around, around, and around, and around. Where do those G1 particles come from that go around the iron filings? Right from here, right from the magnet itself. It then obtains a flow around the iron filings, and it then has its own magnetic field. This causes the filings to take a position like the compass needle, first by G2 gravity. And then that magnetic field causes the repulsion of the streams of iron filing. Each stream now, all lined up, are going to they sort of go against each other. There's not much room here, but if I go clockwise around and around. Well, if I start over here and do it, when they both go the same direction, in the middle they meet and repel. So you can do it this way, clockwise, or do it this way. They're both still clockwise, but they meet, they collide. That causes the repulsion in a magnetic field. Answer: yes, the iron filings do tell us, and these gaps tell us, that they're magnetized, and therefore there is a magnetic field around the magnet, or these wouldn't have gained a magnetic field. Now, iron filings in the compass. Will the position of the iron filings be changed when a compass needle is placed near the magnet? This is quite a complex thing going on here. You've got G1 particles flowing around and through the magnet. You've got G1 particles flowing around and through the filings. And you've got G1 particles flowing around and through the compass needle. Yeah, try to wrap that around your head, having three sets of dynamic flows, all controlled by G2 gravity. It's mind-boggling. In general, G2 gravity, holding atoms together, holding molecules together, holding our body together. Yeah, that's mind-boggling. The compass needle has a strong magnetic field. It could cause the iron filings to move, and the result could be visible. In other words, we tell students, line these things up and you can draw a magnetic field line. But the very fact that you put them there, if you have iron filings along with it, you're actually going to, this is straight. This is, in fact, if you put a big compass like I've shown in previous pictures, that's going to distort the lines. You want to use the smallest compass possible with the smallest needle so that you don't disturb the iron filings. But when you have iron filings and a compass needle around a magnet, you actually almost have Heisenberg's uncertainty principle. You can't measure that line accurately because you're destroying the iron filing lines. What are you doing to the G1 particles flowing around and through the magnet? Pretty strong. It's probably pretty hard to change those, but clearly G1s hitting G1s all over the place, including to separate the lines here. There's a lot of activity, really hard to explain. Okay. So, as I said last time, I went to an internet to find iron filings of battery. You can't find it, so I did it myself. I actually already had here a little container that had iron filings in a plastic case with a lot of iron filings. Unfortunately, too many, I think. And I put the battery down next to it, and it didn't magnetize the iron filings, but it moves the compass needle. Clearly, if there's a weak magnetic field on battery, it's very weak. The battery moves the compass needle by virtue of G2 gravity. But if there is a magnetic field, it's very weak, and I didn't have the proper equipment. To be honest with you, I really need to, not that expensive, invest a little bit of money, take some time to figure it out. One of the interesting points I didn't mention last time was that I showed the compass around a battery that was a free battery, wasn't connected to anything. But a battery that is driving a circuit will have many more G1s flowing through it and could develop a stronger magnetic field if it even had one, because the G2 gravity around it's going to be stronger, and so there's a better potential for a battery to have a magnetic field when it's in a circuit with a lot of G1s flowing through it, strong G2 gravity around it. You can't find any information about it. I was going to have to do more work myself, and I haven't up to this point done that. The conclusion: is there G2 gravity around the magnet and battery? Yes, the movement of the compass needle tells us that there is. It does not tell us there's a magnetic field. There is a magnetic field around a magnet. Yes, the iron filings gives us the answer. To me, that's where the answer comes. I can't prove the field just by a compass needle. I can with the iron filings. Is there a magnetic field around a battery? There could be. But we need to see the pattern of iron filings and the repulsion of the streams of iron filings to prove it. In my mind, until you do that, you really can't prove it. You can suggest it could be there, but you need the iron filings to prove it. Final statement. A G1 particle moves at speed c, has no charge, nor does it have its own magnetic field. It's just a particle. In reality, there's no magnetic field. I continue to call it that because it's the understood terminology. In the particle model, the flow of G1s around and through a magnet is called a magnetic field, even though the particle model has an explanation that is mechanical and gravitational, not magnetic. Still use the term. My name is Bob D. Hilster, and I am your particle model guru. Thank you for your attention.